For lesson 7.1 in BC Calculus, you can see our learning targets. I can find inverses, actually a non-calculus topic. I can take derivatives of inverse functions. Let's get to this definition real quickly. A function f with domain D and range R is a one-to-one function. We could also abbreviate that with 1-1. If whenever a is not equal to b in D, in other words, these are x values right here, and they're different x values. That means these y values right here would have to be different as well. Have two different x values, their corresponding y values must be different. We use a horizontal line test to check if a function is one-to-one. We can see right here if we had a couple of pictures, and if we just had something that looked more like so. If we did a horizontal line test, you can see immediately we'd be in trouble. This would not be one-to-one. The reason is you'd have two different x values that would have the same y value. In other words, if a horizontal line crosses one or more times, your function is not considered a one-to-one function. By way of comparison, any horizontal line drawn on this next curve would, in fact, just intersect just once, so we would have a one-to-one function. Of course, what is always understood is if we're talking about a function, of course, then we're assuming that you already would pass the vertical line test. From a calculus perspective, if a function is strictly increasing or strictly decreasing, then the function is one-to-one. That means that if f prime of x is going to be positive or negative, and we could say greater than or equal to 0 even and get away with this, you can see that you will, in fact, pretty much guarantee that your function would pass the horizontal line test. If your derivative is positive, your function is going upwards. If it's negative, it's going downwards. Let's take a look here. Let f be a function, a one-to-one function with domain and range. The inverse function, we could call that g, could be written as f -1 of x. That has nothing to do with an exponent. And that function would have domain R and range D. You can see that the domain and the range are actually switching. So we could say y equals f of x if and only if g of y would equal x. So what you will see for a real quick theorem, and again, this is still pre-calculus and Algebra 2 review, if g is your inverse function, g of f of x would equal x. In other words, g would undo the work that f did. By way of comparison, if you had a g of y and if you took f of g of y, the f and the g would cancel out. You'd be left with y for every y in R. So let's go ahead and see if we could actually get down to business and find some inverses. For example 1, it says, let's let f of x be equal to 6x plus 1. Could we find the inverse function? Well, first of all, you might wonder why we even, we're talking about derivatives in the beginning. If we took a real quick derivative here, you could see that we'd be at 6, which is always greater than or equal to 0. Our function would always be increasing. So that means it's a one-to-one function. One-to-one functions, like we saw up here, a one-to-one function means you can find an inverse. So you can find that inverse. F of x is really y. And you might remember how we did this long ago. We switch x and y. Wherever we see a y, we replace it with an x. Wherever we see an x, we replace that with a y. And then we solve for our new y. We get that new y alone. We can minus a 1 from both sides. And then we can divide by a 6. And what you have just done is you have found your inverse function. Inverse functions, I always think of as the undo button. They reverse the work that the original function f is doing. And very, very, very importantly, they actually will also have a very special relationship. They will always have a reflection. F and F inverse are reflections about the line y equals x. So that can be helpful for you. Let's take a look at example number 2. As we look at example number 2, you can see that f of x is equal to 1 minus x squared, but so very importantly, they're telling you that x is less than or equal to 0. Well, we know we have an upside down parabola. We know that that 1 there would move us up 1. But we only have half of a parabola. This parabola is only opening up towards that left-hand side where x is negative. We can't even plug in values like x equals 1 or x equals 2. Why is that so important? If we had a full parabola, we wouldn't have a one-to-one function. Right now we do. So we can find our inverse. Let's say we had 1 minus our x squared. And what you can do is switch your x and your y. And I'm going to solve for my new y. I'm going to bring this y squared to the left side. Simultaneously, I'm going to subtract an x. And of course, as you're solving, when you take your square roots, what will puzzle kids is they'll say, well, I'm coming up with 2 distinct answers here. I'm getting y equals the positive square root of x minus 1 and y equals the negative square root of x minus 1. And understandably, kids will think, well, my word, which one do I choose? You're not going to choose both. Guys, the fact that if you had the original problem, x is less than or equal to 0, you could switch the x and the y here. And that is so critical. Without even needing to look at a graph, you could say y must be negative. And that's going to help you know that y has to equal the negative square root of 1 minus x. Then what? We could rewrite that as f inverse in that form. And that would be your inverse function. Now we need to take a look at the calculus behind what is occurring. Let's go to that second page right now. And a picture is so incredibly important. This picture is worth memorizing, having a very good idea as to what that could look like. So let's just say that you've got a function f of x, and I'm just writing it very abstractly. But I also have some arbitrary point, a comma b. Now remember, we also said that there should be the line y equals x whenever we're dealing with a inverse function. And if I were to have g, of course, g is going to look something more like that. B comma a would be that reflection that we'd have over the line y equals x. And we're going to get into calculus right now. Understanding that there are 2 different points is so very, very, very important. It's one of the most important parts of this lesson. Because we're going to talk about derivatives. And of course, derivatives are tangent lines. And if I have a derivative on f, that means I have a derivative on f inverse, which we could call the function g. And we have the point a comma b on f. We have the point b comma a on g. And notice what this very bold statement is right here. They're saying And this is what you really, really, really want to hold on to. That the derivative of the inverse at point B, and I'm going to highlight that right here, is the reciprocal 1 over the derivative of the original function f at the x value of a. Really importantly, I can't stress this enough, there are two different points, a comma b, b comma a. You're evaluating those derivatives really at two different x values. G prime is evaluated when x is equal to b, and f prime was evaluated to have a tangent line slope at x equals a. Now, we're thinking here, wow, we're making a claim that this tangent line slope is going to be a reciprocal relationship. Well, to help you see it, please remember that M, one of the first things that you would have learned, about slope was that it was change in y over change in x, delta y over delta x. Well, M right here, look, just like I was doing on the front page, I could say to find my inverse, how about I switch x and y? Now, immediately, you're going to see this is a reciprocal slope. It could be like 1 over delta y over delta x is another way to look at it. So that's that reciprocal relationship. So very, very, very important. Please remember just these basics, that we've got 2 points, and we've got two different tangent lines. The two different tangent lines are evaluated at 2 different x values. But the relationship between those 2 lines is a reciprocal relationship. We're about to see this in action when we get to example number 3, and we're going to actually go to a new video to see that.